Hello everyone. In this lecture, we'll be continuing on the dynamics of capillary rise. In the last lecture, we had already derived the above equation that is shown here. This is a nonlinear equation, second order nonlinear equation for the height of the column as it rises in the capillary tube, starting with z is equal to 0 at t equal to 0. Now, what we want to do in this lecture is to analyze various regimes because an analytical solution of this equation is not possible. Let's basically consider a graph like this where we're looking at variation of z with time. We already know that at large time we should expect the Jordan's height, which is z is equal to h. Okay, and if you remember, h is nothing but 2 gamma cos theta by rho GA, where the angle theta is the angle that the meniscus makes with the wall of the tube. Now we are already also anticipated that this the curve that we should expect may look something like this. Initially there will be a nonlinear regime, and then there will be a linear regime, and there will be some kind of a decay. Let us see if we can actually get these regimes from this equation. Now we can roughly divide this graph into a couple of small regimes here. Now at short times, early on in the rise, we expect added mass to be important, and this will be inertia dominated. This inertia will persist for a little longer. Within this is the inertial regime, and the height we can say roughly is z goes like h nu or hv. Beyond this height, we expect viscous forces to kick in, and therefore we should expect that there are two more regimes. We have an early viscous regime and we have a late viscous regime. So this we can say is early viscous, and this is late viscous. Again, the analysis will be similar to the one carried out by Professor John Bush at MIT. Now let's look at the inertial regime, and we will always keep going back to this equation, and let's look at what are the various terms of this equation. Now the first thing in inertial regime is to note when does it occur. Inertial regime occurs at very short times. By what do we mean by short times? It is a time which is much smaller than the viscous time scale. We've already seen the viscous time scale, T mu, and therefore we can say inertial regime is when T is much smaller than T viscous. And when this happens, we have the inertial regime, and let's look at what happens to the equation in this regime. When you are in the inertial regime, Z is small. We also have Z dot is also small. Z dot is also very close to 0, and Z is also very close to 0, right? And viscous terms themselves are not important. Viscous forces are unimportant, and the fluid has not really risen much in the column, and therefore gravity is also unimportant. Now further, the velocity is small, dynamic pressure terms is also small. So Z is small, therefore Z dot square term is small. Now let's look at this equation here. If you look at all the terms of this equation, Z is small. When I say small, it is small comparable to the second term, which is 7 by 6a on the left hand side. So the dominant balance On the left hand side, you have 7 by 6a times z double dot. That's the left hand side. And the right hand side, gravity is small, viscous terms are small, and the dynamic pressure is small. So you cannot ignore surface tension, because ultimately that is the driving force, and therefore we keep this balances 2 gamma cos theta by rho a. And when we do this, what do we get? We can simply integrate this equation twice. We get z of t goes like 6 by 7 gamma cos theta by rho a square times t square. We have a t square over 2 that we get from integration, which cancels the 2 in the numerator. So this is the expression that we get. Okay. So this is the first result that we've got. Let's call this as A. Okay. This is consistent with what we have shown in the figure here. So this is Z goes like t square. Right. Now let's look at the next case. We are still in the inertial regime. Inertia has still not died off. But now, as it rises, as the column accelerates upwards, from an initial velocity of z dot equal to 0, z dot square becomes important. The column is rising up, so it's essentially picking up speed, and when it's picking up speed, the dynamic pressure term eventually becomes important. And as this happens, the balance now becomes, so here this is when z becomes larger than 7 by 6a, and when this happens, we have dominates inertia. And why would that happen? Because z double dot goes to 0, so acceleration is going to 0. Now the balance would be 7, the surface tension term 2 gamma cos theta by rho a minus half z dot square is approximately 0. So what have we done here? We're equating the surface tension term to the last term here, because the left hand side is practically very small. Okay. And when this happens, I can integrate this. I have z dot square, z dot, which I can call it as a velocity u, goes like 4 gamma cos theta by rho a whole power half, and therefore I can say z of t goes like 4 gamma cos theta by rho a times time. Okay, this is my second result. We'll call this as equation number 2. Okay, so we have a linear regime that comes in. So this is z goes like linearly increases with time. So here the velocity is constant because z is increasing with t, so z dot is constant. Acceleration is negligible. Okay, and so now we have reached a time where viscous terms start becoming important. We've gone past the entry length region, and we have entered into the fully developed region. So now we will enter the viscous regime. So viscous regime kicks in when T becomes larger and comparable to T mu. Okay. So let's look at the equation and understand what are the terms that become important in the viscous regime. Now, inertial terms are already very small. So we expect surface tension, of course, to be important because that is the driving force. Now the column has risen to a certain height, so gravity may not be negligible. So we'll retain the gravity term. And then we also have the viscous term that has become important. Okay. So now let's look at these three terms and see how do I write down the equation of motion for this case. Now in this case, we have surface tension term, and then we have the viscous term, and finally gravity term are all equally important. Okay. And we know that the static height of the capillary tube is 2 gamma cos theta rho Ga. Why is this important? Because now we are approaching this final height. Okay, so that is the height that is shown with the red dashed line at the very top. We are approaching this final height, and we want to see a natural length scale is emerging, and we want to see how does this length scale also enter the analysis. Okay. Now let's look at the rewrite this equation. Okay, how do we rewrite this equation? We can actually say, now we want to divide the entire equation by G, and if we do that, what do we get now? We have H, the left hand side, minus Z will be 8 mu Z Z dot by rho Ga square, and therefore I have Z dot will be rho Ga square by 8 mu Z of H minus Z, and this will further give me rho Ga square by 8 mu of H by Z minus 1. This is the equation for Z dot. Okay. Let's define a new time scale here. Defining a time scale Tg, which is going to be a balance of viscous forces to gravitational forces, that will be 8 mu H by rho Ga square. We will also define a non-dimensional variable Z star, which is Z by H, and a non-dimensional time T star, which is T by Tg. What do we have here? We have Z dot, which is nothing but dz by dt. This becomes H by Tg dz star by dt star. Okay. If I substitute it, what do I get? I get H by Tg dz star by dt star will be rho Ga square by 8 mu. H by Z is 1 by Z star minus 1. Okay. Now we can substitute the expressions for H and the Tg that we just defined, and we get dz star by dt star will be 1 minus Z star by Z star, and this gives me dt star will be Z star by 1 minus Z star of dz star. Okay, I can rewrite this as the numerator that is there here can be written as z star minus 1 plus 1 by 1 minus z star dz star, which is nothing but minus 1 plus 1 by 1 minus z star of dz star. I can integrate on both sides. What do I get now? I get t star will be minus z star minus natural log of 1 minus z star. That's the result I get. So this is a fairly complicated equation involving z and t. It's certainly much simpler than what we had here, but we still don't have a simple closed form expression for how z varies with time. Okay, but what do we know is that as z approaches h, z star approaches 1. It approaches 1 from below, and notice that when z star approaches 1 from below, the right hand side, if you see, the logarithmic term diverges, and this means that this happens. This means that this occurs when t star goes to infinity. Okay, so in other words, you can also say when t star goes to infinity, z star approaches 1. In other words, z reaches the final height h. Okay, so now that we have this expression, we can now divide this into two parts, okay, to understand the various regimes. So we'll first define what I call as the early viscous regime. Let's look at the early viscous regime. And when does this occur? This occurs when z star is still much smaller than 1. In other words, z is still sufficiently away from the final height h. We can write this as z is much smaller than h. Okay. And when this happens, I can use Taylor series expansion to write down the logarithm of 1 minus z star will go like minus z star square by 2 and so on. This is Taylor series. Okay. And therefore, if I substitute this, what do I get? I get t star is minus z star minus of the logarithm of this term, which is minus z star square by 2 and so on. And if I cancel out the z star term, then what do I get? I get t star goes like z star square over 2, and therefore I can say z star goes like root of t star. Okay, but z star is nothing but z by h. This goes like root of t by tg. That's the non-dimensional term. Okay, again you can substitute the expressions for h and tg. Okay, we get a relation z of t goes like gamma a cos theta by 2 mu with a t inside the square root. This is a well-known result. It's called the Washburn's law. Okay, so z goes like root t, and so let's go back and look at our thing. So here we have z goes like root t. We had predicted in the last lecture that we should expect z going like t power alpha, where alpha is less than 1, and now we find that the value of alpha is half. So it's a slower growth than z goes like t. Okay, and so now let's look at the final regime, which is the late viscous regime. In this regime, basically we are reaching Z goes like Z star is much closer to 1, okay, or rather I should say Z star approaches 1 from below, okay. And if you look at this equation that I have in green, T star, let me highlight that equation. If you look at this equation, now when Z star approaches 1, T becomes very large, is something that we have seen. Now if you look at the two terms on the right hand side, what are the two terms that we have? We have minus Z star and we have logarithmic term. The logarithm term becomes very large compared to Z star, and therefore this equation approximately becomes T star is approximately minus logarithm of 1 minus Z star. These are the two dominant terms, and therefore I have logarithm of 1 minus Z star goes like minus T star. 1 minus Z star is exponential of minus T star. Z star is 1 minus exponential of minus T star. Or in other words, Z over H is equal to 1 minus e power minus T by Tg. Or in other words, Z of T is equal to H of 1 minus e power minus T by Tg. This is the exponential decay. So we have got basically the fourth regime, which is exponential decay. So this one you can say is Z goes like H into 1 minus e power minus T over a length nu time scale Tg. That's an exponential decaying regime. Okay, so these are the four regimes that we have got. So again, just to quickly summarize what we've seen in the lecture is we started with a nonlinear governing equation for the height of the column in the capillary tube. We've basically got four regimes. The first regime is basically a T square regime. Okay, Z goes like T square. This is an early rise where added mass effect becomes important. Then we have an inertial regime where dynamic pressure becomes important, where acceleration has become less important. And so now the fluid would, the column would rise with a linear, at a linear rate, increases linearly in time. Then the viscous regime kicks in. And once viscous regime becomes important, we can again divide them into two regimes. We have the Washburn law where the column height slows down, it grows, but it continues to grow like root T. And finally, we have an exponentially decaying regime. Okay. Now you can further say static regime is finally the last regime in some. It's not a regime per se; it's the final height. As T goes to infinity, clearly you can see Z of T approaches H. So this is the final height, and we know that this is the Jourens law. It reaches the final height, which is given by the Jourens law. So what we have done in these two lectures is we have started with a simple problem of capillary rise in a tube. We have taken all the dominant forces into account: surface tension, gravity, added mass, dynamic pressure, and viscous terms. We have constructed a simple model for the fluid rising in a capillary tube, and then we've derived a nonlinear equation for the height, and we've analyzed this equation in different regimes. Okay. If one has to basically get the full height of this capillary, the full evolution of the height of the column, one has to solve it numerically, okay, which is clearly beyond the scope of a lecture like this. So in the next set of lectures, we'll be looking at thin films, we'll be looking at instabilities, and we'll be looking at jets. Thank you.